Ska jag ta och börja med en liten presentation om oss på Ariadne, vilka vi är. Vi är ett ingenjörsföretag som hjälper med digitala simuleringar och beräkningar. Vi vill hjälpa er att jobba effektivare och öka konkurrenskraften och öka lönsamheten. Just det här med toleransanalys så kan man faktiskt spara mycket pengar. Om vi tittar på bilden nere till höger med våra kompetensområden så utgår vi från den digitala CAD-modellen i mitten och precis nedanför det så står det MBD, Model Based Definition. Det är någonting vi jobbar hårt med just nu faktiskt. Vi vill hjälpa företag att jobba effektivare som sagt. Och vi kommer se idag de här fördelarna med Model Based Definition. För har man toleranserna i 3D-modellen så läser ju programmet in dem helt automatiskt och man slipper all manuell inblandning. Och det går ju mycket snabbare då om man minimerar riskerna för fel. Våra affärsområden är ju mjukvara, konsultuppdrag och utbildning. Vi är ju då återförsäljare för PTC, Sigmetrix och Sigmetrix som har verktyg för toleransanalys. Capvidia som har Model Based Definition och automatisk kvalitetskontroll. Anarch som har Model Based Definition och intelligent informationshantering. Konsultuppdrag. Vi kör Model Based Definition Workshop. Vi kör toleransanalys och hållfasthetsberäkningar och formulärskorsning och mycket mera. Så det är bara att höra av sig om ni har någonting som ni behöver hjälp med. Utbildningar. Vi är då licensierade partner med PTC så vi har Creo-utbildningarna. Och resten av utbildningarna som jag visar här har vi utvecklat själva som vi är väldigt stolta över som är då grunderna i toleransanalys som jag kommer att prata mer om senare. Vi har formuläge och vi har FEM för konstruktörer och design för 3D-print. Men vad är då toleransanalys? Om vi går in på den biten. För konstruktören, han sitter ju i en perfekt värld så att men så ser det inte ut efter tillverkning när man får detaljen i handen. Det finns ju alltid en variation efter tillverkningen. Och sen när man monterar ihop alla detaljer så blir det då en kedja av toleranser. Och det kan bli ganska stora variationer i slutändan. Och få svaret så gör man ju då en analys på alla toleranser. Och man får fram vilka dimensioner som påverkar mer eller mindre. Och man kan då optimera toleranserna. Varför ska man göra en toleransanalys då? Ja, det är ju för att få ett svar på hur och vart man kan spara tid och pengar. För det blir ju färre prototyper och det gäller ju att vara snabbare än sina konkurrenter och snabbare ut på marknaden. Man får en ökad kvalitet och minskad support och det blir ju att man får nöjdare kunder helt enkelt. Sen har vi då den här klassiska kampen mellan konstruktion och tillverkning där. Det är ju då vilka toleranser krävs. För konstruktörerna, han vill ju ha då snäva toleranser för att säkerställa funktion och oftast tar man i lite för mycket där och produktion eller tillverkning, de vill ju släppa på toleranserna för att sänka produktionskostnader till exempel. Men då genom att göra en toleransanalys så kan man då få den här vågen och få så att man får optimala toleranser så att båda två blir nöjda. Det var en väldigt kort introduktion här så att jag lämnar över till Felix som får köra ett demo på det här.
Yes, I'll just share my screen. Am I sharing, Patrick?
Yes, perfect.
Okay, great. All right, welcome everyone. My name is Felix. I'm an application engineer here at Ariadne Engineering. I'm mostly involved with tolerance analysis. And today I'm going to demonstrate easy tolerance analysis for CTOL, for Creo parametric, and it's fully integrated in Creo parametric. And the benefit with this is that we can reuse a lot of the information we already have in the 3D model. For example, assembly constraints or product manufacturing information. So right now I'm showing the product we are working with today, a small electric motor, and I'll just show a section view so we can see what's happening inside. And for the first part, we're going to investigate the gap right here between the bearing and the casing. And you can see there's already a washer inside, but we want to see how much this gap can vary if it gets bigger or smaller to just fit an appropriate washer inside. So I'm just going to start the application. You can see it here, easy tolerance analysis. And we get a new toolbar. And I'll just get started and define the first stack up or specification. So I just select the surfaces. So one side of the bearing and then the surface on the casing. Then I'll place my annotation. So that's the nominal gap, 1.92 millimeter. And then EasyTol automatically looks at the assembly constraints I have defined in my 3D model and finds the tolerance loop, like here. So it will highlight all the parts which are part of my loop and the contacting surfaces. And if I just click OK, it will display the stack up here on the right-hand side and the nominal dimensions in the graphics interface. Now the only thing left to do is I'll just name my stack up. So this is the washer gap and put in some requirements. So in this case, I want to be within plus minus 0.5 millimeter. And just like that, we've defined our analysis. So that was a really quick and easy process. And what we get down here, that's our worst case result. So in a worst case scenario, the gap can be up to 1 millimeter larger than nominal or 0.8 millimeters smaller. So that barely took a few minutes. But let's see what else we have here. Here in the table, we can see all the parts and tolerances which are part of our stack up. So for example, you can see if I hover over the first name right here, which is just the part name, it will highlight the bearing. So that's the first component in the chain. And here's basically the width of the bearing. So from one side to the other. And the dimension is, so the bearing is nominally 14 millimeters thick. And it has a tolerance of a maximum of 14 and a minimum of 13.9 millimeter. And you can see the little chain icon right here, which means this tolerance is imported directly from the 3D model. So if we have that information, we'll just use that for our tolerance analysis. And then you, for example, you can see here, the next part, that's the shaft. And here we have a linear dimension plus minus 0.3 millimeters. And then, for example, here we have a geometric tolerance. So we support all kinds of tolerances. All right, and that brings us to our worst case result at the bottom. But the great benefit here is we don't only get the worst case result, but we can also look at the statistical result. So I can change the analysis type up here, and depending on your needs, you can quickly switch between worst case, root sum squared, or some statistical metrics. For example, capability, sigma value, percentage of yield, or defects per million opportunities. I'll now show capability, or CPK, which is a very common metric used in several industries. And it basically says how well you fulfill your requirements for any given specification. So I'll just switch to statistical capability, and we can see the result window down here changes quite a bit. All right, so now instead of just a bar, we get a certain distribution. So here in the middle, these values or results are more likely, and then of course, further out, the likelihood decreases. We have a target quality we want to reach. Then we have our current quality, So that's basically how well we fulfill the specification with the current tolerances and requirements. And that's currently set at 0.88, which is not quite that good. And then we have a mean. So the mean value of the gap is a little bit larger than the nominal value. And then, of course, the standard deviation. So how do we actually get this distribution? Well, you can see here in the table, we get a new column called capability. And that basically tells us how well our supplier fulfills any given tolerance. You can see by default, they're all set to 1.0, which is a more conservative estimate. But if we know we have a better supplier, we can just go in here and change that and say maybe, well, our supplier is good, so he'll create any given dimension to a capability of 1.33. And you can see that immediately impacts our result down here. I'll just go back. All right, so we said currently we're only getting a capability of 0.88, which is not quite as good as we want to have it. And for this demonstration, we want to have a target capability or target quality of 1.33, which is a very common used metric, maybe in the automotive industry. In other industries, for example, defense or medical, you might need a higher quality because the results of failure will be much worse. So there we might have a target capability of 1.67. But for this, a target quality of 1.33 is good enough. So how do we reach that? Well, in this case, we need to tighten some of our tolerances. But, well, we have quite a few in the chain. Which ones? So for this, we're just going to switch to the contribution tab right here. And we see all the tolerances in the chain and how much they contribute to the variation. And we can see here, these two linear dimensions together, they're nearly 90%. So they are our optimal candidate for tightening tolerances. So I'll just look for the linear dimension right here, currently set to plus minus 0.3. And I'll change that a little bit to plus minus 0.15. So I'm going to tighten the tolerance a little bit. And you can see the contribution it's gotten a lot lower. And the great benefit here is that this tolerance is directly linked to our 3D model. So every change I make will also be changed in the 3D annotation. So after I've done tightening or loosening all the tolerances, I don't need to go back and do the same in the 3D model. So that saves me a lot of work. So I'll just find the other one right here, and I'll also set that to plus minus 0.15. All right, let's have another look at the result. Very good. You can see we are much better now. So we've reached a target quality of 1.51, which is above the one I wanted, which was 1.33. So in this case, we might actually be able to loosen some other tolerances to decrease manufacturing cost. And again, in this case, I want to loosen the ones which are at the very bottom. All right, for example, this bearing. Currently, we have an upper limit of 15.9, a lower limit of 15.8. Let's see what happens if I change that to 15.75. All right, see, gotten a little bit worse, but still above our target. So this is an easy way to just have a look what happens if I change tolerances. Can I loosen them somewhere to decrease manufacturing costs, or do I need to tighten them somewhere? And I get immediate feedback on how that affects our specification. Of course, you often don't only have one specification for any given product, but multiple. So I'll just add another one to our model. So I just define a new stack up. And in this case, I want to investigate the gap between the rotor and the stator up here. Again, I'll just place my annotation. And you can see in this case, due to how the assembly constraints work out, it cannot find a path through the model to create my tolerance loop. So I have to define that manually. But again, this is a very simple and intuitive process. The first thing we do is just define all the parts which are part of my stacker. You can see the rotor is already transparent, so that's the first part in the chain. The next part would be the shaft, the bearing, the casing, the shell, and then the stator. Next step is to define the mechanical interfaces. So how do parts connect? So the rotor connects to the shaft here, and shaft to bearing right here. And you can see this is super intuitive and really fast. Just build up the tolerance loop. And just like that, we've defined our stacker. Again, it will display all the nominal dimensions in the graphical interface. And you can see here, we're currently looking at the axis alignment, but I wanted to have a look at the gap. So I'll just change our attachment. And now you can see up here between the rotor and stator, we have a nominal gap of 0.33 millimeters. And then I'll just name that rotor stator gap. All right, again, we are importing a lot of the tolerances, except for up here, you can see we're actually missing some. So for example, right here, the outer diameter of the shaft, instead of having a symmetric tolerance, we can just change that, for example, to a plus minus. We like that, plus 0 and minus 0.05, so I'll maintain the gap. And you can see, even if we don't import the tolerances, we can add them manually within EasyTol. So again, you've got the choice. If you have 3D tolerances, that's great. We'll reuse them. If not, that's no problem. We'll just add tolerances to our model manually within EasyTol. And that's a super quick and easy process as well. So for example, here we can add a geometric tolerance, position, runout, coaxiality in this case might be appropriate. Tolerance value 0.1. Do I want a material modifier? What's the datum? Again, do I want a material modifier on the datum? And just like that, we've added a coaxiality tolerance. So we support size dimensions, geometric tolerances, linear dimensions, everything you need for your one-dimensional analysis. And then again, down here, we get the result. You can see in our case, right now, we get another message down here. And it says, calculated results are ignoring potentially significant 3D effects. What does that mean? It basically means that our analysis might not be fully one-dimensional. So we might have 2D or 3D effects, which could affect our result. And this is a note for you to kind of have another look. Are there any 2D or 3D effects I need to consider? And maybe do I need to do a full 2D or 3D analysis? Maybe do I need to use another tool? Just that you have that on your mind. All right, if I defined all my necessary specifications, I might want to share what I've discovered or what I've done with some of my colleagues. So in this case, we can generate a report with EasyTol. I'll just take a few screenshots for the report of each individual stack up I created, and then maybe one for the title page. And then I just click on Generate Report, give it a name, report, and I'll save it as an HTML file, which you can share with your colleagues. This is how it looks. You can see our specifications in the main tab, a summary of all the specifications we created, the washer gap, the rotor stator gap, and then of course for each specification right here, all the tolerances in the loop and the result we wanted to show. And the same for the stator gap. And of course, you also get a list of the contributors. So this is a very fast and easy way to share your analysis with your colleagues. And after you're done, you'll just save your model. So just save your Creo assembly, and all our EasyTol information will be stored within the assembly file. So you don't need to have an extra file you need to access every time. No, you have all the information right there within the model. And every time I do some design changes to any of the parts, maybe I make the shaft a bit longer, or I increase the diameter of the rotor. Then if I activate my application again, all those changes will automatically be within the analysis. So I don't need to update any spreadsheets. No, I just start the application, everything will be updated automatically. So this was a very small, very short introduction into easy tolerance analysis for Creo parametric.